Hi everyone, welcome to our first TAP seminar of this academic year, and thank you for joining us. So this is our first externally advertised seminar in the series, so everyone could join us today. So just a quick reminder before we start, so for everyone who's joining us online, could you please keep your microphones muted during the presentation? So we'll have some time for questions at the end, so you can either add your question into the chat and we can read it out for you, or you can raise your hand and ask your question directly at the end. Just to note that we are recording the seminar, so if you do speak during the session, you might be on the recording. Okay, so today we're delighted to welcome Dr. Gordon Forbes from King's College London. Gordon's recently completed his PhD, during which he was developing prognostic models for predicting long-term outcomes for autistic children. So as part of this, Gordon undertook an IPD meta-analysis, and so today he's going to be sharing his insights about using IPD meta-analysis to model between study heterogeneity when developing a prediction model with a continuous outcome. Okay, over to you.
Thank you. So today I'll be talking about modelling between study heterogeneity. I did prediction modelling with an IPD meta-analysis. Sorry, just standing and plugs and things. And this is really going to focus my work, sort of have both an applied aspect in developing the models and also a statistical aspect where I looked at some stats methods, and this is going to really focus on the stats side of things, and really on quite a niche part of statistical modelling. So I hope this will be super interesting for the statisticians in the room. If anyone's not a statistician, sorry. Here we go. So this sort of the methodological work was really motivated by an applied problem I was working on, and I was looking to develop prediction models for co-occurring mental health challenges for use with autistic children. And autism is a relatively rare condition, so sort of approximately 1% or 2% of the population are autistic. And this has led to sort of many small data sets, partly because of the fragmentation of research funding. So you can't get a big grant for doing research in autism in the same way you can with more common conditions. And then also where there are large data sets, so if you look at a large general population study, like the cohort study, only a small fraction of those will be autistic. So you might have a study with 10,000 people, but it has 100 autistic people in it. And so this leads to sort of, when you're looking at data sort of on longer term outcomes for autistic children, this leads to you having sort of lots and lots of small data sets to work with. The other thing with autism is you've got this ever-changing context, and I think this is there with a lot of health outcomes. I think it's particularly strong in mental health research, which a lot of my work relates to. And with autism in particular, there are a couple of things. First, sort of over the last maybe, let's say, 10, 20 years, which is a period in lots of the data I use was affected, but in changes in diagnostic criteria. So the sort of things you needed to meet to be classified as autistic changed. I think it was around 2013. And then that would have taken some time to be rolled out across clinical practice. And the second thing is, alongside this change in diagnostic criteria, there's just this huge change in who's been recognised as autistic. So I think if you go back to the 90s, most people, maybe not most, but a significant proportion of people diagnosed with autism also had co-occurring intellectual disabilities. And you sort of had this sort of distinction was drawn between people with autism and intellectual disabilities, and people used to call it high functioning autism or Asperger's, where people had autism and didn't have their sort of normal levels of cognitive functioning. And then since then, it's been realised that this sort of dichotomy isn't there, and many more people who previously would have been labelled high-functioning autistic have been diagnosed. So the proportion of people with intellectual disability with autism has gone right down. And so you've got this change in population. And if we go 10 years into the future, I don't know what the population of autistic people will look like. And when you go to clinical conferences in autism, people sort of stand up and they give presentations and they say, like, everything we thought we knew to be true about autism isn't true. And they can go through this list of things. Like, we used to think it was only boys, we used to think it was lots of intellectual disability. And so you've got this sort of real change in who is autistic and the population that's going to be used for your models. And so sort of generalizability across sort of different settings is really key. And then the final thing on the sort of outcomes we're using is when you're looking at mental health conditions, you've got the choice of using sort of symptom scores. So you can look at depression symptoms, or you can look at diagnosis. So you can look at diagnosed depression. And particularly in adolescence, which was a time period of outcomes we were looking at, the diagnosis isn't super reliable because people don't necessarily get diagnoses for existing mental health conditions. And this might be due to sort of restrictions in clinical services. So there are quite long waiting lists for CAM services at the moment if you want to get diagnosed. And it can also be because of something called diagnostic overshadowing. So you might go to clinical services, you get diagnosed with autism, they won't necessarily diagnose you with an anxiety condition as well, because your anxiety symptoms may be seen as linked to autism. So we don't have this reliability of diagnosis. And then also, for autistic people, high symptom levels are relevant even if it isn't a diagnosis. So if you're an autistic person, if you're struggling with anxiety symptoms, even if you don't meet the criteria for a generalized anxiety disorder for whatever reason, you're still struggling with anxiety symptoms. So it's still very relevant. And so based on this, I decided to do two things. I thought I'd use an individual participant data meta-analysis to develop the models, so bringing together lots of these small data sets. And we'd also develop models for continuous symptom scores, so develop models for outcomes on continuous scales rather than binary sort of depression, or not just depression, we looked at other conditions as well, but rather than binary diagnoses. And in the blurb of the talk, I had this slide late. I reread it after I made the slides, but I saw that I said I'd say something generally about prediction modeling and continuous outcomes. And I think this is something which during this work has become apparent to me. Is lots of the literature on prediction modeling focuses on binary outcomes or time to event outcomes. And this is because lots of things in health we're interested in predicting are those. But continuous outcomes are also everywhere and very relevant to patients. So this might be symptom scores, this might be quality of life, this could be, I don't know, other continuous measures of health. We see them everywhere. And what you often see, so when I was doing background research for this project, I was looking for models of psychopathology, not just in autistic people, but elsewhere. You often see people dichotomize the symptom scores. So they have the same data that I'd have, and then they define people as having depression or not depression based on cutoff. And this is where you can all boo. Don't worry, the rest of this talk won't be interactive. As a statistician, I hate dichotomizing because you lose statistical information, and all of a sudden you go from needing a sample size of one thing, maybe a few hundred, to a sample size of a few thousand. But there are other limitations as well. You don't always have common cut points for your outcomes. So you see people dichotomizing. One person might dichotomize at the median, one person might use a centile, one person might use a clinical cutoff established in a small study in Sweden in 2013. And it means that people develop models for these outcomes, but the outcome then isn't the same when people want to apply them. They say they're developing a model for depression, but actually what they mean is a depression score on CBCL above the median, which isn't necessarily depression. But I don't know, yeah, there's a discussion. A lot of my clinical colleagues love dichotomized outcomes, so it's clinical relevance, and I don't agree with that. But yeah, that's a sort of slightly separate discussion. But prediction modeling in continuous outcomes is very, like, it's the same thing as prediction modeling with binary outcomes, prediction modeling with time to event outcomes. You have slightly different performance measures. You end up using R squared, which is, you can sort of say is equivalent to discrimination. Root mean squared error sort of behaves slightly different to your sort of squared error metric in binary outcomes with Breer score because the variance isn't linked to it. Calibration is still very relevant for continuous outcomes. And then another part is that sort of the way you characterize uncertainty in predictions. And I'm not going to talk about this anymore today, but this is something I'm also interested in. So when you make risk predictions, and the reason why often people prefer predicting risks over classification is you communicate some sort of uncertainty. So if you say someone's got a 60% risk or a 55% risk, you're saying, yeah, the outcome's more likely to happen than it's not, but it's also quite likely not to happen. And there's both a prediction there about what's going to happen and a sense of the uncertainty. Whereas with continuous outcomes, if I say you're going to have a 7 on a score from 1 to 10, I'm not telling you whether I think, okay, but it's probably going to be between 2 and 9, or whether I'm saying that it's going to be between 6 and 8. And with this, you can, I think the best way to approach it is using prediction intervals. So sort of communicate that uncertainty. But I think there are differing opinions, and that hasn't become widespread in use. If you're doing machine learning, confusingly, you call modeling continuous outcomes regression, rather than meaning that you're actually doing linear regression. But if anyone's into machine learning, it's like, what's he talking about? I'm talking about the regression problem. Yeah, and much of this is relevant to continuous outcomes. So I won't talk any more about this, but if anyone else is sort of interested in this, has opinions or questions, please ask. And so next, there are two things. One is continuous outcomes, one's IPD meta-analysis. And I'm sort of assuming that lots of people in this audience will be familiar with this. But the sort of basic approach to prediction modeling using IPD meta-analysis is you generally use a one-stage modeling approach. So you model the pooled data directly rather than sort of putting individual models and meta-analyzing afterwards. Although there's no sort of reason why that might not be a good approach. It's just more complicated. You can use this technique, which I really like, called internal-external cross-validation, to obtain study-specific estimates of model performance. So for each of your studies in your data set, you hold one out, fit the model on the rest of the studies, and then use that study essentially as an external validation set. And you do this with each of your studies in turn. So it looks a bit like cross-validation. So it looks like you're doing internal validation, but you're, rather than using random splits of the data, you're using these sort of splits by study. So in that sense, it's external validation. So people call it internal, external cross-validation. And once you get these sort of study-specific estimates of model performance, you can then meta-analyze those. And if you use a random effects meta-analysis, you can then get an estimate of between study heterogeneity and model performance. And some people say that this can be an indication as to how well your model will generalize. So if you see low between study heterogeneity across your participating studies, that might give you confidence that the model performance is similar across lots of different settings, particularly if you've got quite a diverse set of studies, and so it might generalize well when applied. And if you see high between study heterogeneity, that means that you're seeing different model performance in each of your settings that you have data from to develop the model, and that might translate when you go on to apply it. And when doing prediction modeling in clustered data, you end up with this slightly complicated set of choices around where you do things conditional on study. So you can do your modeling conditional on study or marginal to study. So you can adjust for study in your modeling. You can make predictions conditional on study or marginal to study. So you can use study-specific terms when making predictions, or you can average over study-specific terms. And then you can also estimate model performance conditional study or marginal to study. So you can do model performance conditional on study using something like internal external cross-validation, or you could just estimate your model performance when you're on a pooled data set. So I'm looking at overall performance, which you could do, I guess, with conventional internal validation, or if you have an external data set, you could just use the data straight. And in this talk, I'm going to sort of touch on these different modeling and prediction approaches, but I'm going to focus on conditional model performance, because this is something which I was really interested in, because in this area, this sort of question of generalizability in autism, will we see these models developed on these diverse set of studies? Will they work in the future? Do they work both in settings where they're high levels of intellectual disability and in settings where they're low levels of intellectual disability, for example? And there's a really good paper on this from a few years ago, which sort of lays all this out. And so the sort of general setting I'm going to be talking about is we're developing a prediction model for a continuous outcome. We've got data from an IPD meta-analysis. We're interested in model performance conditional study. We're also interested in between study heterogeneity and model performance. We want to use our model not in one of the clusters or the studies that we use to develop the data, which are these sort of hodgepodge of research studies that have happened over the last sort of 10, 15 years, but in sort of clinical practice today, which is a new setting, different from that which provided the data. And then the modeling I did, I just used linear models. We didn't do any sort of machine learning, partly because of sample size, partly because of other reasons. And also, I'm only going to talk about modeling heterogeneity in intercept terms. So there's no reason why you couldn't have model between study heterogeneity and your predictor effects. Things that get more complicated when it came to use the model. But following, sort of to keep things simple, we just sort of look at intercept terms today, and I'll touch on some ideas around what this might mean for if you want to model heterogeneity in more complex ways at the end of the talk. And there's quite a lot of work already done in this area, particularly sort of focusing on the general sort of modeling in cluster data rather than in IPD meta-analysis specifically. And there's sort of two things which sort of two gaps in this work, I think. First is that they mostly look at conditional predictions in existing clusters. So sort of they're generally simulation studies, they simulate some data, they make predictions in these existing clusters, they estimate the intercepts in those clusters, and they don't look at, okay, what happens if you're using new data, if you've got new data available to estimate intercepts. And then mostly look at binary outcomes, or they exclusively look at binary outcomes, and it's all simulation. And one of the nice things of working with continuous outcomes is the maths is easier, and sometimes you can find formulas for things where with binary outcomes you can only have numerical approximations. So we've got these two choices. So how are we going to model heterogeneity? So we can use fixed effects models, random intercept models, or we could not model heterogeneity at all. And then what are we going to do when we make predictions in new studies? So we're going to make a marginal study or conditional studies to estimate a new intercept in new settings. And so a lot of what follows actually just comes from sort of basic differences between fixed intercept models and random intercept models. Before starting this work, I thought I knew a reasonable amount about fixed intercepts and random intercept models, but it turned out I really didn't. And these results have been known sort of for a really long time. And so I think what I'm going to talk about today is sort of taking these results, which I think are well-known statistical results, properties of these models, and really applying them and thinking what are the implications of these for prediction modeling and IPD meta-analysis. So with a fixed intercept model, you sort of add lots of parameters when you start modeling study effects, one for each study. With a random intercept model, you're just estimating your random intercept variance. Random intercept models struggle when you have a small number of studies. You get underestimation of your random intercept variance. Use of between study information. So random intercept models, and if you model not adjusting for study, uses both between and within study information. I'll talk a bit more about this later and what that means, whereas fixed intercept models only use within study information. Because of this, fixed intercept models can't be used to model study level predictors, whereas random intercept models can. And you can also model study level predicted models not adjusting for study. Put that exclamation mark there, so I don't know if it's a great idea, and I didn't want to put a big green tick in front of everyone, but I don't see why you wouldn't. Random intercept models come with additional assumptions around the independence of study-specific intercepts and predictors. And fixed intercept models don't need this assumption. If you don't model study intercepts, this will sort of, if you've got a predictor which is correlated with study, I mean, we're doing prediction modeling, so we're not talking about causality, but you essentially get confounding between the two, and it can lead to bias in predictions. Random intercept models, you can have distributional assumptions about your intercepts. You typically assume they're normally distributed. And then random intercept models, you can also use this thing called empirical Bayes prediction when you're predicting your new intercept. So if you want to give a value to that random intercept in a new cluster, which is something I'm going to look at. This is sort of the key difference when making predictions. And these differences, what follows sort of comes from these differences between the models. And if you're doing a meta-analysis of, if you're doing like an IPD meta-analysis, let's say you're looking at the treatment interactions, there's a whole load of literature looking at these sort of differences between taking like a fixed approach and a random intercept approach. And a lot of what I'm going to talk about also sort of relates to that and follows some way from that. So there's sort of three things I'm going to touch on for the remainder of the talk. So first is sort of what happens to model performance if you estimate study intercepts badly when making predictions. Secondly is the impact of empirical Bayes predictions when modeling in new data. And then finally is this sort of use of within and between information and sort of thinking about this confounding by cluster. I can call it confounding, it's prediction modeling. But yeah, the sort of additional assumptions that random intercept models make over fixed intercept models. For the next bit, I'm assuming our data is coming from this sort of correctly specified random intercept model. So we've got normally distributed random intercept terms, normally distributed errors, and all these things are nicely independent where they need to be. And you can then, because it's continuous outcomes, you can then write down your prediction errors really easily. So if you predict marginal to study, so you just use an estimate of the overall intercept, and if we've just written one predictor here, you can have as many as you wanted. Of your beta parameter, then you'll get sort of this prediction error. And if you make your prediction conditional on study, and you additionally have a sort of alpha j, a study-specific intercept, this will be your prediction error. And the sort of, if you average over a particular study, providing you've got an unbiased estimate of your overall intercepts, of your beta parameters, your errors will have mean 0. You just end up with this study-specific intercept as your sort of expected error. And likewise, if you model conditional on study, you've got the difference between that study-specific intercept and your estimate of that study intercept as your error. And so if that is also an unbiased estimate on average, that will go to 0. And so what we see, what this sort of translates to is when you make predictions marginal to study, the average error for any study is equal to the study's intercept. So across studies, these average 0. But you get additional variance when looking across studies in errors from this estimation. So you'll get the variance in errors due to random chance, but also you get the variance in errors due to these study-specific intercepts. So this leads to between-study heterogeneity and calibration in the large. And the amount of between-study heterogeneity, if you simulate from this sort of simple model we've got, is just equal to the variance of the, or I don't know if it'll be exactly equal, but it's approximately the variance of the random intercept terms. And when you make predictions conditional on study, the average errors are equal to the error in the study intercept estimate. So if your study intercepts are estimated well, that will be 0. And so you'll see no between study heterogeneity and calibration in the large. But if you use something which doesn't estimate it perfect, if you've got a bad estimate of that, then you can still see some heterogeneity and calibration in the large. And there's a really nice empirical example of this in a paper that a few people in this group worked on a long time ago. I think it was in 2016, so almost 10 years ago, where they're looking at meta-analyzing using an IPD meta-analysis to externally validate a model. And they use 3 different strategies for estimating intercepts. They estimated the intercept in the external validation study. So this is a conditional intercept using sort of the data from the study, so a good estimate of intercepts. And they found really low between study heterogeneity. They used a marginal approach, then an average study intercept, and they found sort of relatively higher between study heterogeneity. And the third approach they used, they took an intercept from a similar study. So like this study's got similar prevalence, we'll use that intercept. So it's better than an average, but not as good as re-estimating it. And you find this sort of level of between study heterogeneity and calibration in the large in between the two. So this was really nice to see that sort of my thinking actually matches what's done before. And it makes me think that probably some of the people in this group probably understand what I'm talking about, if not sort of explicitly, but at least very intuitively, because it's something that sort of has come up in work. And so the sort of implications for modeling, okay, so when making predictions, we know if we've got a good intercept of intercepts, it reduces between study heterogeneity. But why does this matter when I'm doing modeling? And this is because of this empirical Bayes prediction. So your choice of model can affect how you estimate your intercepts when making predictions in new data. And these ticks are in the wrong place. You can't do an empirical Bayes prediction with a fixed study intercept. That should be a big red cross there. Let's quickly move on. So empirical Bayes prediction can be used to estimate random effects from mixed effects models. This isn't just random intercepts, this isn't just continuous outcomes. It can be used this is what you use with any mixed effects model. And what you do is you use the knowledge of your random effects distribution as a prior. So if you're using it for your random intercept model, you know from your model, your intercept is normally distributed with the variance that you've estimated in your modeling, and you use this as your prior when predicting new intercepts. And I think it's not a pure application of Bayes' theorem, which is why they call it empirical Bayes rather than just Bayes. But But this prior acts as the penalisation term. So it adds bias but reduces the variance. So I think it's proved to have a lower mean squared error than if you just use a conventional estimate of the intercepts. And for random intercept models for continuous outcomes, there's an analytic formula, which is why I like working with continuous outcomes. So the sort of top line on the right up here is just what you'd use to, if you're re-estimating an intercept. Generally, you take the predictions, you look at the sort of the effects of all the betas, and you can estimate an intercept in a particular study. So this way I formulated it, merges sort of all intercepts and the study-specific intercepts. When doing an empirical Bayes prediction, you just multiply it by this penalisation term. And this is how it comes out for continuous outcomes of random intercept models. I think it can be more complicated with more complicated mixed effects models. And this penalisation term is given by this equation here on the right. And this sort of, if you look at this, if you're familiar with an equation for an ICC, this looks very similar, but it's got this study size in the bottom right corner. So what you see is the degree of penalisation is dependent on the sort of ICC, the degree of clustering, and also the size of the study. And you can plot it. So this is just curves. They look like I've drawn them with a Sharpie. These are curves of this equation here on the right. And so you can see when you've got really small clusters, so 1 is no penalisation, so high is less penalisation, low is more penalisation. When you've got small studies, you get more penalisation. And if you've got 1,000 people, if you've got data on 1,000 people when estimating your new intercepts, your penalisation is almost 0. Or not almost, your sort of multiplicative factor is 1, so there's no effect of penalisation. So this is what we'd expect. When you don't have a lot of information to estimate your new intercept, the empirical Bayes prediction pulls it back towards 0. When you do, it says, yeah, your data is reliable. And what we see, so if we look at this numerically, when ICCs are sort of below 0.05, which is what we see a lot in clustered data, it might be different in IPD meta-analysis. If you've got sort of a reasonable amount of data, 50, 200 or more people to estimate your intercept, you sort of get quite small levels of penalisation. So empirical Bayes predictions become very like the predictions you'd make without empirical Bayes. Whereas so only when you have small amounts of data, you get sort of a meaningful difference from empirical Bayes prediction. And so we ran some simulations. I ran some simulations looking at model performance and looking at the difference between sort of fixed and random intercept models. And these were the results. So the panel on the left is the estimates between study heterogeneity. If we see these sort of average 0 across all the different settings. And the panel on the right is the between study heterogeneity. And we see that we sort of have the expected pattern, which is the marginal predictions when ICC is 0 here. They do really well. So there's no between study heterogeneity in the data generating models. So we see no between study heterogeneity in the calibration in the large. And for higher ICCs, we see more between study heterogeneity. And what we see is oh, I've chopped off a bit of the heading. The dark green, I guess which one's which. One of these is using Bramble and one of these isn't using Bramble. That's the difference between the two green ones. When you use empirical Bayes prediction, if you only have 10 people available to estimate your intercepts, you see reduced between study heterogeneity in most of the settings compared to if you'd used a fixed intercept model, or if you'd re-estimated the intercept in the model, not adjusting for studies. So that would just be your regular intercept updating that you could do applying to the study you're working with. But for larger amounts of data available, and for higher ICCs, the differences between random intercept modeling or fixed intercept model when making predictions. So random intercept modeling using empirical Bayes sort of isn't really meaningful. So it's sort of this advantage you get of random intercept models when using empirical Bayes prediction comes around when you've only got small amounts of data to estimate intercepts in these studies. There are a few, I mentioned at the beginning that random intercept models can underestimate the variance when you have a small number of studies, and for continuous outcomes, 8 studies is no longer like they do quite well with 8 studies. But you do see a few these sort of points where you're seeing high levels of between study heterogeneity, even though you've got sort of a large number of people to estimate the data. I think these outliers are often when the random intercept variance is estimated as 0 incorrectly, and then your empirical Bayes penalty becomes 0, and regardless of how much data you've got, you end up essentially making marginal predictions. So where you get underestimation of the random intercept variance due to small numbers of studies, you end up making predictions more similar to marginal predictions, even when you've got lots of data available. So using empirical Bayes prediction when making predictions with new sort of individual data available in the setting can lead to reduced heterogeneity and calibration in the large when you've got a sort of small degree of clustering and limited data available to estimate new intercepts. Underestimation of the variance can cause problems, and the difference between empirical Bayes and standard intercept estimation are minimal for study sizes over 50, unless you've got very low random intercept variance. So there's sort of interplay between the level of the level of your random intercept variance and how much difference empirical Bayes estimation makes. So when the ICC was 0, estimating new intercepts of small numbers of data, the small amounts of data introduce a lot of between study heterogeneity. So if the true intercept is actually the same as in the development data, but you go and estimate sort of 10 observations from a new data set, you're just making things worse, in a sense. One word of caution. Whilst most mixed effects packages support empirical Bayes prediction in the development data, they largely don't out of sample, apart from GSEN and Stata, people who like structural equation modelling. And whilst with the continuous outcomes, there's an easy analytic result you can use, that isn't the case with binary outcomes. And some of these fail and they give you missing data when you try and predict it. Some of these fail silently and just give you zeros. And I might be wrong, particularly with these R. I'm pretty sure I'm right, but I'm not an expert in mixed modelling packages in R. And there are a lot of ones, they're more than just LME4 and LME, so it might be possible to do. But yeah, just be aware that your software might not, if it's in some binary outcomes, might not support what you want to do. But on the train, my train was delayed on the train all the way here. I was thinking about this, and you could just do a conventional Bayesian estimate using the random intercept variance from your model as a prior and sort of implement it yourself. So relatively straightforward if this was something you wanted to look at. So just to check back in on this, so the final part of the talk, I'm just going to think about this difference we've got where we've got these additional assumptions around independence of study-specific intercepts for random intercept and fixed intercept models and what the implications there are for modelling. Because so far I think we've seen that if I was having to choose between the two, the random intercept model offers some advantages when you've got limited numbers, provided you've got sufficient clusters, if you've got limited data availability when estimating intercepts. And so what am I talking about when I talk about between and within study information? So within study information is the information that comes from the association between the predictor and outcome within each study. And between study information comes from associations between the average predictor in the study and the average outcome across the study. And these can differ. So we've got examples that younger people in a particular study have better outcomes. That's within study information. But if there's some sort of selection mechanism that goes on where studies with older people on average have better outcomes, even though older people individually have worse outcomes, that's between study information. And this can arise if the sort of studies of young people, the only reason young people are in your clinical data sets because they're critically ill for some other reason. They may have much worse outcomes, even if being young generally is related to better outcomes. And this sort of arises a lot in statistics. It's sort of behind the ecological fallacy, where we don't just do our analysis on pooled data sets. And you can sort of have these differences in directions from between and within study information. And fixed effects models only use within study information, whereas random intercept models sort of pool between the two. But again, the degree of pooling is dependent on the degree of clustering and also on study sample size. And And again, because it's continuous outcomes, you can look at formulas for the sort of degree of pooling that goes on between the pooling of between and within study information. So I think these are based on a feasible generalized least squares estimator. So not your standard maximum likelihood or REML, but I think it's fairly similar what you'd get out of those. And what you see is this is a relative contribution of between study information. What you see is that if your degree of clustering in your predictors is low, they mostly use within study information. Or if you've got large studies when you're developing your models, so if you've got some size of 200 continuous outcomes, 1,000, the random intercept models are mostly using within study information. So whilst there's assumptions around the use of between and within study information are important for random intercept models, in lots of the settings where we work in with individual participant data analysis, where you have relatively large studies, and most sort of empirical data has relatively small amounts of clustering, random intercept models are fairly equivalent to fixed intercept models in that they mostly use within study information. And one exception to this might be if you've got a particular predictor that's based around the eligibility criteria for your study. So some of your studies restricted, let's take age, some of your studies say they only recruit people over 50, some of your studies say they only recruit people under 50. You might see sort of artificial, sort of really heavy clustering by studies for some of your predictors. And we ran some simulations again, seeing what impact sort of the assumptions that random intercept models have, what impact those not holding have on model performance. And here we're looking at calibration slope. And so when you see this compounding by cluster, that's what it's called in my head. Economists call it level 2 endogeneity. But what it is, when you see this correlation between your random intercept and your particular predictor, so the left-hand panel, this correlation is 0. When you have this correlation, you see slightly worse calibration slope for random intercept models, which is this blue one, compared to fixed intercept models, which is the yellow one. But that really is only there when we've got really small study sizes. So if we look at the row where we've got a study size of 200, they're very similar. And it's also really only there when your predictor ICC is very high. So these simulations were done just with a single predictor. And I simulated it having an ICC of 0.25, 0.5, or 0.9. So this is the proportion of the variance that's happening between studies. And I think this is quite artificially high. In most of your predictors, you see much more variance within study than between study. So sort of my conclusions from this were you can do simulations where you do show this as a problem, but they're unlikely. This is unlikely to happen in your data unless there's sort of a reason. So sort of be cautious around, be cautious when you've got a high degree of clustering for a predictor. And there's things you can do if you still want to do random intercept modeling. You can use this model called the within between random intercept modeling. This involves centering your predictor at the cluster mean, or the study mean for each study. So if you do IPD meta-analysis of treatment interactions, I think often you center your treatment variable, and this is sort of why this to avoid this. And this is a similar, so you can take a similar approach. And I guess you'd want to do that in a prediction model selectively with a particular predictor you're worried about, and it then gives you the headache of what do you do when you're making predictions. You need to get an average value for that predictor you chose to center. So not necessarily a great solution. The grey box, which really stands out, that's models not adjusting for study. So if you have this correlation between predictor and study, you've got confounding by cluster, and you don't adjust for study, these models share between and within information in different ways to random intercept models, and it's not affected by study size. It's just affected by predictor ICCs. So these models can perform poorly when this is a problem, even when you've got a lot of data, you've got large studies. And this is what we'd expect. If there's sort of, I guess from a causal inference perspective, if you had confounding by a variable in your model and you don't adjust for it, you're going to get bad estimates of your predictor. And we sort of get a similar thing going on here. So this sort of brings me to the end of what I wanted to talk about today. So the sort of conclusions and recommendations. So overall, I think sort of as is known, using marginal prediction is going to lead to between study heterogeneity and calibration in the large. And where you see that, it's best to re-estimate intercepts. And I think this is sort of known prediction modeling of IPD meta-analysis, which if you're seeing this sort of between study heterogeneity and model performance, you might have to do model updating when you apply your model. Empirical based prediction can offer advantages, provided your random intercept variance is estimated well when there's a small amount of data available to make new predictions. And there's no need to pick, I think. Like you can fit a fixed effects model and publish that, and you can also fit a random intercept model and publish that. And then people, if they're deploying your model, they can choose which one they're going to use. And if they've got the technical ability and they know they've only got a small amount of data to estimate an intercept, they might use empirical Bayes estimates from your random intercept model. Or they could just do the standard thing you do when re-estimating an intercept from a fixed intercept model. Yeah, there are limited software implementations, and particularly once you start working with binary outcomes and your software might fail silently. And the sort of final thing is you might want to use a random intercept model for your modeling because you want to model study level covariates. You might have a binary outcome, you might be worried, you can't do these empirical Bayes estimations, but there's no need to use empirical Bayes estimates when predicting intercepts of the random intercept model. You can just re-estimate your intercept in your new setting in exactly the same way you do with any model. So you calculate the predictions in the study, see what the average of the predictions is, and calculate the offset. And then sort of unconfounded by cluster. So random intercept models have these additional assumptions, but they mostly use within study information, provided studies are large and there's only a moderate or small degree of clustering in predictors. So I'd say they're quite robust to this sort of confounded by cluster, I call it, or level 2 endogeneity. And if you don't adjust for study, your model's more susceptible to sort of this level 2 confounded by study or level 2 heterogeneity. So sort of from this, I'd say, even if you're planning on using marginal predictions when you deploy your model, it's worth modeling study. Because it can sort of mess up these associations, and particularly when you've got these sort of key predictors, for which the distribution does differ between studies. So yeah, because of whatever selection or whatever's going on in your designs. A few limitations. This work also sort of heavily based on simulation, and I've sort of assumed quite ideal models. I haven't thought about what if your distribution of intercepts differs from your development data and when you're deploying it. I've sort of haven't looked at between study heterogeneity and predictor associations. Does that make re-estimating your intercepts more or less important? Other assumptions around the intercept models, informative cluster sizes, haven't looked at that. To focus on conditional model performance, you might get different results for marginal model performance. And there's a paper where they looked at sort of confounded by cluster and the impact on marginal model performance, and they get a slightly different pattern of results. And the sort of final thing with these sort of simulation-based results is like, what do you actually expect from your data? So do my simulation scenarios really match what you'll see in your data? And there are systematic reviews of ICCs and cluster data, and they're typically very low. They sort of come out between 0 and 0.05. So you see lots of like 0.003 and things like that. And there's a few, this one's from primary care. In IPD meta-analysis, I think you probably have higher between study heterogeneity and conventional cluster data because you've got these differences in design. It's not just multi-center data, that studies might be at different times or use different eligibility criteria or whatever. And then also, this sort of what level of confounding by cluster. So in the plot I showed you, there's a 0.5 correlation between intercepts and a predictor, which I think is probably unreasonably high. So I think the sort of issues around even confounding by cluster in practice might end up being quite small. And then I'll just finish with some sort of thoughts of what I think the implications of this might be for things I didn't look at. So binary outcomes, I think, would see similar patterns. I think empirical Bayes would help with estimation of intercepts. Sample size is always higher with binary outcomes, particularly if you've got rare outcomes. So this helping hand you get from empirical Bayes prediction might be more useful. But there are limited software implementations, which sort of dampens that. But there are sort of more complexities of binary outcomes. And yeah, there's publications highlighting that you can't just average over intercepts in the same way as you can with continuous outcomes to get marginal predictions. You've got to integrate over them properly, and this is sort of because of non-collapsibility. And yeah, sort of even defining clustering of binary outcomes becomes more complicated. Implications if you're modeling more terms, so just looked at between study heterogeneity and intercepts. If you also model between, if you also allowed for if you use a mixed effects model and you allow for a random effect for a key predictor, you could also use empirical Bayes predictions to re-estimate that predictor association. And I expect you to see a similar pattern. So when you've got small data, it might help. And this might be relevant in a lot of my work with mental health symptoms. Your best predictor, and really only important predictor. You've got more things in your model because you have to, but the one you need is baseline symptom score, and that predicts outcome symptom score. And so you might find that if you fit a mixed effects model where you had a random intercept and a random effect for baseline symptom score, you could then re-estimate that in new settings with limited amounts of data using empirical Bayes estimations to help you. But I don't know if anyone really starts looking at random effects and more terms when doing prediction modeling and IPDMA meta-analysis. Finally, machine learning. So all of this relies on this linearity assumption, which I think is unreasonably effective in health data. Like, it seems like a terrible idea, but linear models always do remarkably well. And if we're using more flexible models, with just everything would get really difficult. And I don't know, I haven't looked. Someone might have looked at this and done some work on this. There might be an answer, but for me, if there's a model that doesn't have a simple study parameter, you can't make marginal predictions. If you put it in your model, you can't average over anything, because what are you averaging over? But there might be ways to do it. But if you don't model study, you might be more susceptible to bias, and there's correlation between predictors and studies. So this might be something you need to be cautious about. So yeah, that's everything. So yeah, thank you all for listening. I'd like to thank, I don't know if Richard Riley's listening online or is here, but I spoke to him right at the beginning of this. I had this wild idea of all the things I was going to look at. And he was like, just look at random intercepts, it's probably enough there. And that really helped me out. And this work's all been funded by the NIHR. Yeah.
We haven't got any questions in the chat so far, so if we got any questions, anyone want to raise their hand, or anyone on person got any questions? Diana, do you want to unmute yourself?
Hi, Gordon. It's very nice and it's really, really good, and I appreciate the talk. I think that for me, like, the question that I wanted to ask is basically, how do you summarize the whole thing? Like, when, at what ICC, at what size, people should really stop not using any random or fixed intercept?
I think to give like I think I'd avoid giving an actual number on that. I think I probably could run some more detailed simulations, maybe come up with a cutoff, but I think it's sort of, for this with continuous outcomes, I think it was in most of the simulation studies when you got 50 people, things started looking very similar between empirical Bayes predictions from random intercept models and fixed effects models. And if you go higher than that, if you got 100 people too, I didn't simulate that. 100 I simulated at 200, but by 200 it's sort of very similar. And with ICCs, which of course can be published from your model, so you know how much clustering there was by study in the development data. Again, I think sort of below, I only simulated 0.05, but somewhere between those two, I think is where you'd probably want to draw a line.
I have a specific question. To implement this model,
Yeah.
it could be like data derived from clinical trial, or can be like data derived from the observational data as well.
No, you can use anything. And well, I guess if we're looking at doing longitudinal prediction modeling, it's helpful if the data sets are longitudinal. But I use cohort studies for this because you're not necessarily interested in treatment effect. So yeah, I modeled sort of without thinking about treatment. Sort of you could use data from clinical trials if it's available because it's convenient. People have often done quite good studies, but it wouldn't necessarily be more helpful. It might even have weird selection things going on.
Do we have any more questions online?
I had a question similar to the first question. So you were saying that a bunch of the packages that are out there don't allow us to do out sample variable base. But then you said that, yeah, overfish, whatever the limit was you got, that you were getting similar to a standard intercept estimation anyway. So we wouldn't need empirical.
Yeah, I think so. So for continuous outcomes, the formula there, you can write that yourself really easily. So you can do empirical based predictions from that without the software supporting you. If you were doing this in a binary outcome, or if you had a more complicated mixed effects model, it gets harder. And so I think provided if you've got loads of data when you're estimating your intercept, or not even like a moderate amount of data available from the setting you're working in, and you're estimating your data in the visual data, I don't think it makes much difference. So it's only this situation where you've got a small, often you might not have any data in the setting you're looking to implement, and then you've got to do something else as well. So it's only this setting where you've got a small amount of data, this sort of Goldilocks zone, and you've got the technical ability to do it, and you can just do a Bayesian estimation of the intercept using your random intercept variance as your prior. I haven't thought that through that much, but I'm sure it's possible. And that's when it can help. It's like penalized regression, I guess, in that sense. Like it's not going to fix your problems, but if it's just right, it might.
Just right. Yeah. So you didn't. So you picked those ends. You didn't look at. I'm interested in whether we could use some existing sample size calculations to decide maybe how the n we need for that intercept estimation.
Yeah. So you could, I guess, if you were looking at bringing it into sample size calculations, you'd say, okay, we get if we don't use empirical estimation, we get acceptable re-estimation of intercepts with 100 people, let's say, based on whatever criteria you're using. And then you might find that those criteria are met using empirical based estimation at a lower point. And I think, the reason why it's difficult giving thresholds is you have this interplay between like ICC and sample size. So 10 might be enough if you've got a ICC of 0.05, but it might not be enough if it's 0.025. So you could bring that together in sample size calculations, and it might lower the minimum you need.
Do you have a feel for what people are doing at the moment? Are they ignoring the clustering, or are they using one?
I don't know. I think people are either ignoring it or using fixed intercepts.
Right.
Because I haven't seen much on the software side of empirical. Like most people do prediction models, modeling for binary data, and it took me a bit of, I was like, oh brilliant, I just run my simulations of the binary outcome, and I was like, hang on, I can't. So like I haven't seen a lot on that, so I don't think people are, because otherwise they'd be bumping into this issue. Or they're using marginal predictions, possibly unknowingly, because they think they're predicting new intercepts, but actually their software package just predicts zeros, which it does sometimes.
About time to event albums?
I think that'll suffer the same complexities as binary outcomes. And I think, you've got the same sort of non-collapsibility when you're starting a lot of survival modeling. And you've got the same, I haven't looked at packages for multi-level survival modeling to see what they do. So I don't know, but I expect it to be similar. I think the reason these implementations don't exist is because you need to get these empirical based predictions, you need to integrate over the likelihood in some way that I don't fully understand. And GSEM instead does it, and it does like adaptive quadrature to do it. So you're going to use like numerical integration, which is there for clusters in your development data, because that's done when you're estimating the model. But in a new cluster, this is this. I don't really understand it, but it's sort of the.
And so the small data issue you mentioned at the start, that it's quite rare. There's
Yeah.
small studies that have been funded
Yeah.
around. So this is a good advert for IPDMA analysis, right? And is that how you got the funding in the first place? Was the proposal that you could pull all this together?
Yeah. Yeah, so this project was funded as I'm going to develop prediction models for autistic children. This is like clinical benefit, and there's some interesting methodological avenues.
Yeah.
And that's what the NHR went for.
And so my question is, in terms of your applied project, how successful has that been, and how small were your samples that you could estimate?
So we looked at a few different outcomes. We had sort of up to 8 or 9 studies, each ranging from like 50 to 100. So I think one data set was just under 1,000, one data set was just under 600 people by the time we brought everyone together, which, because with prediction modeling continuous outcomes, is enough data. And we fit models which have quite good performance. I think, yeah, differed. So the R squared for some outcomes was 0.7, for functional ones, for psychopathology was more like 0.4, but they sort of looked like you can make meaningful predictions. And then there was a lot of between study heterogeneity and model performance. Leaving us with models where we're like, these models work like this, but who knows what will happen if they're sort of externally validated in a new setting.
Yes. So when you fit in the random effects models, some of the times you've got a small number of clusters.
Yeah.
Now, in the clustertron literature, normally we would have small sample corrections.
Yeah.
I'm just wondering whether you included anything, or whether there was anything in the relevant literature around what to do, or.
So I didn't.
Yeah.
I'm just thinking there's lots of the small. I'm thinking the small sample corrections when you do class randomized trial can relate to sort of degrees of freedom and your standard error estimation. So relate to your confidence intervals, which isn't necessarily such an issue when developing prediction models, because you're more interested just in your parameter estimates. So I compared using REML to classic maximum likelihood estimation, which gives you a better estimate of your variances when you've got small samples, but I didn't apply any of the corrections, but I'm not sure whether they would have made a difference. So I think the Kenwood Rogers is a degrees of freedom correction, which we didn't use the degrees of freedom from the model. Where we did use them, or where I did use them, is then when you're doing a meta-analysis of your study-specific model estimates, you can then use your the HKJT, whatever the sort of standard adjustments you do there, which I think take into account the sort of number of studies.
Okay, we're just about done up with time now. Shall we thank Gordon again?